All right, let's go. Number 5. The eternal void that wasn't empty. Nothing is not as simple as it sounds. When physicists say that before the Big Bang there may have been nothing, they don't mean the nothing you picture when you close your eyes. They mean a quantum vacuum, a seething, unstable, mathematically structured state of pure potential in which the laws of physics exist, but no matter, no energy, no space, and no time have yet materialized. And here is the part that should stop you. A quantum vacuum is inherently unstable. It is not a resting state, it is a loaded gun. Quantum field theory tells us that empty space at the quantum level is never truly empty. Virtual particles flicker in and out of existence constantly, borrowing energy from the vacuum and repaying it on timescales governed by the Heisenberg uncertainty principle. In a true quantum vacuum before the Big Bang, the same process applied to the vacuum state itself. Given infinite time, and given that a timeless quantum vacuum has no mechanism preventing quantum fluctuations from occurring, the probability of a fluctuation large enough to nucleate an entire universe approaches 1. The physicist Alexander Vilenkin formalized this in 1982, describing the universe as having tunneled into existence from a state of literally nothing through a process called quantum tunneling from nothing. The mathematics describes a universe with zero total energy, where the positive energy of matter and radiation is precisely cancelled by the negative energy of the gravitational field, meaning the universe cost nothing to create and needed nothing to permit it. The nothing that preceded our universe was not empty in any comfortable sense. It was a quantum mechanical state governed by equations containing the latent possibility of everything. And at some moment that cannot be assigned a time, because time did not yet exist, it became unstable enough to produce us. Number 4. A previous universe collapsed, and we are the debris. Our Big Bang may have been someone else's Big Crunch. The cyclic cosmology model, developed in its most rigorous modern form by Paul Steinhardt and Neil Turok as the ekpyrotic universe, proposes that what we call the beginning was not a beginning at all, but a transition. In this framework, our universe and a parallel universe exist as three-dimensional membranes, called branes, embedded in a higher dimensional space. These branes move through the extra dimension, and periodically they collide. When they collide, the kinetic energy of the impact is converted into the hot, dense plasma of matter and radiation that we identify as the Big Bang. The collision does not destroy either brane. It sets them vibrating, and over trillions of years they cool, expand, and empty out until quantum forces between them slow their separation and draw them back together for the next collision. In this model, the Big Bang was not the first event. It was the latest in a sequence with no identified beginning. The previous universe, if it can be called that, was not our universe running in reverse. It was a different brane, a different three-dimensional cosmos with its own physics, its own matter, its own elapsed history that ended not in fire, but in a slow, cold expansion until it struck us. The evidence left behind by this collision would be imprinted in the cosmic microwave background as specific patterns of non-Gaussianness and gravitational waves with a very particular spectrum. The Steinhardt-Turok model predicts a gravitational wave background with a distinct signature different from inflationary models. We are currently building the instruments to look. If the pattern is there, the universe before ours left a fingerprint in our sky, a scar from the collision that made us. Number 3. Time ran backwards, and we can't tell. Before the Big Bang, the arrow of time may have pointed the other way. The CPT symmetric universe model, proposed by physicists Latham Boyle, Kieran Thin, and Neil Turok in 2018, offers one of the most mathematically elegant and physically disturbing pre-Big Bang scenarios in modern cosmology. The model begins with an observation about the standard model of particle physics. The combined symmetry of charge conjugation, parity reversal, and time reversal, known as CPT symmetry, is believed to be an exact symmetry of nature. Boyle and colleagues showed that the Big Bang can be understood as a CPT mirror point, a moment of perfect symmetry between two universes.
On one side of the Big Bang is our universe, expanding forward in time with matter dominating over antimatter. On the other side, extending backward in time from the same singularity, is a mirror universe composed predominantly of antimatter, contracting from our past toward the Big Bang that we would describe as the future. Both universes emerge from the same point. Both are real. Neither came first. The Big Bang is not the beginning of time. It is the center point of a CPT symmetric structure, with time running in opposite directions on either side, like the two halves of an hourglass. From inside our universe, the mirror universe before the Big Bang looks like it is running backward, from high entropy toward low entropy, from dispersed matter toward a singularity. But an observer in that universe would experience time exactly as we do, moving from their past toward their future, which is our past. The singularity they approach is our origin. Their entire cosmic history occurred in what we would call the time before the beginning, and they would never know we exist any more than we knew about them until someone thought to look for the symmetry. Number 2. Inflation never started because it never stopped. The universe we see may be one accident inside an engine that has been running forever. Eternal inflation is not a theory about what came before the Big Bang in the conventional sense. It is a theory that reframes the question entirely. In standard inflationary cosmology, the very early universe underwent a period of exponential expansion driven by a scalar field called the inflaton, which eventually decayed into the hot plasma of the Big Bang. Eternal inflation, developed by Alexander Vilenkin and Andrei Linde in the 1980s, extends this. In most of the inflating spacetime, the inflaton field does not decay. Quantum fluctuations continuously regenerate the inflationary expansion faster than any region can stop inflating. Only in rare pockets does the inflaton decay, and each such pocket produces a hot Big Bang and evolves into a universe. Our universe is one such pocket. Outside it, inflation continues, endlessly producing new universes, a fractal foam of spacetime in which Big Bangs are events that happen constantly, in every direction, at every moment, in a background that has always been and always will be inflating. In eternal inflation, there is no before the Big Bang for our universe because the process that produced our Big Bang has no beginning. The inflating background spacetime has existed for infinite time, or more precisely, the concept of a beginning does not apply to it the way it applies to our pocket. Every universe in the eternal inflation landscape began with a Big Bang. None of them was the first. The question of what came before our Big Bang dissolves into the recognition that our Big Bang was not a cosmological origin. It was a local event, one of an uncountable number, embedded in a structure that has no origin we can point to and no end we can foresee.
Number 1. Nothing came before, and the question is illegal. The most disturbing answer is that before doesn't apply. This is not a rhetorical dodge. It is a precise mathematical statement about the structure of time itself, and it was made by two of the greatest physicists of the 20th century. In 1983, Stephen Hawking and James Hartle proposed the no-boundary wave function of the universe, a quantum cosmological model in which the universe has no initial boundary, no edge in time from which it began. The model uses a mathematical technique called a Wick rotation, replacing real time with imaginary time in the equations of quantum gravity. In imaginary time, the geometry of the early universe is not a sharp point, a singularity with a defined beginning, but a smooth, closed, finite surface, like the surface of a sphere. A sphere has no edge. It has no point you can identify as the beginning. Every point on its surface is geometrically equivalent. In the Hartle-Hawking model, the early universe in imaginary time is precisely this, a smooth, boundaryless geometry in which the concept of a prior moment does not exist any more than it makes sense to ask what is south of the South Pole.
When you ask what came before the Big Bang in this model, the answer is not that something existed and we don't know what it was. The answer is that the grammatical structure of the question contains an assumption that time extended through the Big Bang and continues before it that is simply false. Time itself emerged with the universe. Before the Big Bang, time did not slow down or reverse or thin out. It ended. Not as a wall, not as a boundary, but as a geometric smoothing, a rounding of the corner of space-time into a closed surface where the concept of before becomes as meaningless as asking for the address of a location 1 meter north of the North Pole. The universe did not begin, it simply has no earlier, and that is not an answer, that is the shape of the limit of the question itself.